Good afternoon. So actually this will be our 21st lecture, so that means we have crossed the midpoint since the course is supposed to is made up of 40 lectures. So we are roughly halfway through the course, almost exactly. So today, perhaps in keeping with that, we will actually start a new topic. But first, as usual, let us just recap what we were doing last time. We were looking at so last time we were finishing our discussion on convolutional codes, and I spoke of the condition needed to ensure that catastrophic error propagation does not take place for a general k by n convolutional code. And since this was in the nature of more of cataloging rather than actually a detailed derivation, I skipped the proofs, and then after that I showed you how you can decode the Viterbi, how you can apply Viterbi decoding even when you want to decode the convolutional code over an additive wide Gaussian noise channel. So we went through that, and then I gave you a couple of formula that you can use to actually upper bound the bit error probability of the Viterbi decoder, and the two formulas correspond respectively to the two different types of channels that we will be encountering. Okay. So that is about where we were, and there was just one item that I thought I should clarify here, is that in these formulae you have this in the formula you have for the AWGN channel you have this D free term that actually appears in the expression, and I just thought I would spend a couple of minutes clarifying that. Okay, so let me just put down the title of our today's lecture, which is the Generalized Distributive Law. Now what I am doing today is I am actually switching tablet PCs. So I am trying to get used to the new writing surface. It is a little bit different from the one I was using earlier, so I might try to write slow until I get used to it. Let us begin with a recap. So we talked about CEP, catastrophic error propagation, in a general rate k by n convolutional code, and then I talked about Viterbi decoding, over the AWGN channel, and then finally I gave you expressions to compute bit error probability of the Viterbi decoder and as I said earlier, before I begin, just a clarification. So in this in our previous expression we ran into this term D free. What exactly does that mean? And I will just keep the explanation very brief. um, now one way of explaining it is that since as you know every path in the trellis corresponds to a code word, and if this trellis is of finite length, that is where you look at the number of branches that you actually see. So, 1, 2, 3, 4, 5, 6, 7, 8, but if there were an infinite number of branches and that would be the infinite trellis, and what we are talking about in D free is the minimum distance, minimum Hamming distance between a pair of distinct code words in the expanded trellis. And as you might imagine, the minimum distance since it is a linear code, you can always try to find the code word of minimum Hamming weight. And as you can imagine, if you just keep going amongst stay amongst the all 0 states, then you will get Hamming weight 0. So, any non-zero code word must deviate from this all 0 path, and as you can imagine, it will try to get the minimum distance. You will actually deviate as little as possible. For example, here is a deviation that gets you very quickly back to the all 0 path, and the Hamming weight that you actually incur is 2 plus 1 plus 2, which is 5. So, this suggests that the minimum Hamming distance between a pair of distinct code words, which is the minimum Hamming weight of a non-zero code word, is actually 5. So, that is actually the case, and in fact, the way we will verify it is through the power series. So, let me just put that down in writing. D free is the minimum Hamming distance between a pair of distinct code words, and in brackets of infinite length in the convolutional code. As a matter of practice, the way you would actually compute it is from the power series. So, so it can be computed from the power series A and L I D as follows. Set L equal to I equal to 1 to get A and 1 1 D. In this power series, D free is the smallest exponent of D. That appears with a non-zero coefficient, but I guess that is understood. So, we will look at an example. In the example, this was our prototype convolutional code, and we had actually come across this before. So, this was L cubed I d to the 5 divided by 1 minus LID into 1 plus L. Therefore, A and L equal to 1, I equal to 1, D is d to the 5 divided by 1 minus 2d. Once you make the substitution, here you see that L is 1, I is 1 and this is 2. So, it is 1 minus 2d, and as a power series, this expands to d to the 5 into 1 plus 2d plus 4d squared plus 8d cubed and so on, exactly as I had explained before. So, therefore, it follows that d free is equal to 5, and we already saw that on the trellis. So, this is just verifying our earlier observation. Okay. So, that wraps up our discussion on convolutional codes, and it was a little shorter than I normally would do, simply because we have other topics to cover. So, today with that we will move on to discussing a new topic, and I have given I have put down this as the title of our lecture, the Generalized Distributive Law, and that might actually puzzle you. What that really means is that you are going to apply the distributive law, but in a different setting, but in potentially different settings. And okay, so what is the relevance of the distributive law to coding theory? Well, this is all got to do with decoding a code. Decoding is paramount from a practical implementation point of view. From a structural point of view, if building a code with large Hamming distance between distinct code words and large code size, these are very desirable things. But on the other hand, and they affect performance, that is true, but on the other hand, from a practical point of view, you can only use codes that you can actually decode without incurring too much of complexity. So, the recent attention in coding theory has shifted towards codes that can be efficiently decoded. Okay. And now, underpinning some of the recent decoding algorithms is something called message passing. It also goes by the name of belief propagation. Sometimes it is also, you also refer to this by saying that you are actually using you are carrying out iterative decoding. These are all a reference to more or less the same class or same type of decoding algorithms. And so, of course, everybody brings their own perspective to this area. Mine, I am heavily influenced by a very nice article written by a well-known coding theorist. I will give you that reference a little later, and I am going to present it from that point of view, which is slightly mathematical, but not very, as you will see. And the nice thing about it is that it develops the theory in a very nice way, admittedly in an idealistic setting. In practice, things are not ideal, but at least this will give you a reference point and say, well, this in some sense is can be my base reference point. Okay, so it's my starting point, and I can use that to understand, try to understand how things are operated in practice. So, let us discuss the generalized distributive law, which is abbreviated simply by GDL. And I just want to give you some examples to begin with of how the distributive law can actually be used to achieve a savings in computation. I mean, consider the simple computation. Supposing I take A times B plus C, this is A times B plus A times C. Now, if you were to carry out the computation as this is organized on the right hand side, you would actually incur 2 multiplications and 1 addition. On the other hand, if you were to use the distributive law to rewrite it, this computation in this form, then it is just one addition and one multiplication. So, in this very simple example, you have already saved on one operation. That may not seem like a lot, but when the number of variables grows and is very large, then this becomes increasingly more significant. Let us take a look at another example. And in this example, I want to carry out a pair of computations which are alpha x w, which is the sum over y z of x y w and g of x comma z. And the second computation is beta of y, which is the sum over x w z, again of the same product. So, we want to evaluate both of these quantities. Initially, we will treat them separately, but the GDL will look at them together, okay, but we will not worry about that for now. I should give you some additional information. So, the variables w, x, y and z take on values from a common alphabet A of size q. Right. So, that is the first point. And then, so here the summation is over x ranging over all of A, x ranging over all of A, w ranging over all of A, and same with z. Then you might ask, well, what about these functions f and g? So, f and g are both real valued. Okay. So, f the functions f, g are real valued. So, they take on values in the set of real numbers. And now the question is, so the question we are going to ask now is, how many computations do you actually need to compute alpha and beta? Okay. So, let us look once again at this computation. Now, normally what I would do is, if this was a classroom setting, I would ask the students in the class, well, tell me how many computations this requires. And just based on personal experience, it is good to be a little bit careful when you are counting, because one tends to be overconfident and I have made mistakes. So, the way we will actually do this computation is, we will first look at this expression and say, look, I need to compute this function alpha for all possible values of x and w. Now, since x and w take on values from a set of size q, there are q squared possible values for this pair. For every value of x in W, then I look at how many computations I need to actually evaluate this expression over here. And when I look at this, I actually see that what I need to do is there are this summation is a summation over again q squared terms, because there are q possibilities for y and q for z. In every one of these terms there is a multiplication involved, okay? And then after the multiplications have been carried out, since there are q squared terms in the summation, I need to do q squared minus 1 additions. So, the number of operations required to compute alpha so the number of computations required is equal to q squared times q squared plus q squared minus 1. Okay. This thing here represents the multiplications, this represents additions. So, this is 2 q to the 4 minus q squared, and usually it is just the leading term that is people look at. So, it is of order q to the 4. Okay. So, that is the number of computations to compute alpha. Let us do a similar calculation for beta. So, for beta, so beta of y is the sum x w z f of x y w g of x comma z. And again the number of computations is given by q, because there are q values of y for which you want to do the computation, times, now in this case there are q cubed summation terms. For each summation term you need to do one multiplication. Okay. So, this will be this times q cubed plus q cubed minus 1. So, this is 2 q to the 4 minus q. Okay. But you can actually compute these in a fewer number of computations by making use of the distributive law. For example, so let me write invoking the distributive law. So, alpha of x w I can compute by actually summing, taking the summation on z inside and taking the summation on y here. So, I can actually compute this by computing this separately by computing this term separately, that term separately, and if I once I have computed this, what this is going to end up as is some other function which you can call f prime of x w. You can call this g prime of x, and now your computation is just alpha x w is equal to this times this. And you can evaluate how much work is involved in computing this. So, let us look at this. Again, one must be careful in evaluating the number of operations needed. The easiest way I find is to again in such cases is to say, look, I need to do a sub computation, or more exactly I need to do two sub computations, one to actually calculate f prime and one to calculate g prime. Okay. So, let us take care of those first. So, to compute f prime requires, since there are q squared values of these arguments, requires q squared. For each of these q squared I need to sum over q terms. So, that is q minus 1, and then to compute g prime I need here I need to sum, there are q values of x, and for every value of x I have a sum over q terms. So, that is q into q minus 1. But I am not done yet, because at the end of that I have computed f prime and g prime. Now, I need to compute alpha, and there are q squared values of x w for which I have to evaluate this. For every pair here I need to do one multiplication, and for alpha therefore, I need an additional q squared operations. So, if I put all of this together, okay, so if I put all of this together and add it up, so the total number of computations is now equal to q cubed minus q squared plus q squared minus q plus q squared. So, I am just adding the three terms, and what I will end up with is these cancel. So, I end up with q cubed plus q squared minus q, because these terms cancel. Right. Now, this should be compared against, so this result here should be compared against our earlier count, which was 2 q 4 minus q squared. So, you can see that we have reduced the number of computations. So, I will write in brackets versus 2 q 4 minus q squared earlier. So, now we are slowly beginning to see how the distributive law comes into play. Now, similarly, one can actually reduce the number of computations needed to compute beta. I will do that a little bit quickly, since the idea should be clear. So, beta of y x w z f of x y w g of x z. So, we will sum over z here, then we will multiply by f x y w and then sum over W and then I have an outer sum over X. So, let me call this just like we did last time G prime of X, and let me call this F prime of X y, and then we are summing over that to get rid of the dependence on X. So, the total number of computations is equal to first I am going to count the number of computations needed to compute F prime, then G prime, then the whole thing. So, this is q squared into q minus 1 plus q into q minus 1 plus q into q plus q minus 1. So, basically this is the number of computations that you need to compute F prime, this G prime, and once you have both F prime and G prime, then this is a single summation which requires q, this many number of computations. So, the total is therefore q cubed, that is the q cubed term, okay. So, q cubed minus q squared plus q squared minus q plus 2q squared minus q. Okay. So, we cancel this and to get a total of q cubed plus 2q squared minus 2q. Again, we have achieved a savings in comparison with the number of computations that we needed on the last, because earlier we had estimated this at 2q4 minus q. So, this is versus 2q4 minus q. Now, in these particular instances, it was fairly easy to see how one could actually organize the computation taking advantage of the distributive law. But if there are a very large number of variables, then it becomes very difficult to do that and it is not practical. So, what the GDL tells you to do is, it tells you that sometimes you can actually organize them by making use of a graph. So, what you do is you associate a graph to this computation and then you use an algorithm on the graph which automatically carries out the distributive law. Okay, so, that is what we are going to do next. However, just as was the case with our development of coding theory, we will spend a little bit of time getting a little bit of mathematics out of the way, because that this whole algorithm, a key point in this whole entire algorithm is that the distributive law can be applied in more other settings other than the one that we are accustomed to. Okay. And that setting turns out to be the setting of algebraic structures which are known as semi-rings. So, let us talk about, so we will take a slight detour and talk about semi-rings. So, what is a semi-ring? So, definition: a semi-ring R plus dot is a set R along with two operations plus and dot, under which the following properties hold. And those properties are: 1, we require that under addition we must have closure, we must have closure, we must have that the operation is associative, there must be an identity element, and then the operation must be commutative. So, you need these 4. Now, what does closure mean? Closure means that if you add 2 elements, then it must be back in the set. So, this applies to addition and R. Okay. So, that means if you think about the structure R under plus, then this structure must have the property of closure. That is, if you add 2 elements in the semi-ring, you get back something in the semi-ring. Then the way you group elements together while adding should not make a difference. There is an identity element and we will call that the 0, and addition should be commutative, that is A plus B is the same as B plus A. And I am not spelling this out because we have already encountered these terms in our earlier discussion on rings. Now, you look at this and say, this really looks familiar, and it does. In fact, when we were actually talking about groups, we encountered these same axioms. There is just one difference, and that difference is that if you look here, down here, when we defined groups, there was an additional property that was required, and that property was the property of the additive inverse. So, except for the fact that a semi-ring need not possess the additive inverse, under addition it has all the other remaining axioms that go into making a group, an abelian group, abelian or commutative group. So, we will just make a note of that. Note that the additive inverse is not required. It could be there, but is not required. Okay, that is as far as addition goes. Then, and we will look at examples shortly. Secondly, under multiplication, that is R must satisfy the properties of, again you must have the property of closure under multiplication. Multiplication must be associative. There must be the identity element, and multiplication must be commutative. Again you look at this and say, well, again it looks like the inverse is not required. That is true. Even under multiplication you do not require an inverse, but that is perhaps not as surprising as was in the earlier case, because after all, when we studied rings, rings were objects which commonly did not contain a multiplicative inverse. Okay, so we have encountered this kind of a situation before. So again note that that multiplication is not multiplicative inverses. Multiplicative inverses need not exist, and then so these properties are very similar to what you would have in the case of a ring. By the way, the identity element for addition is 0, for multiplication it is called 1. And another thing that I think I should point out is that a semi-ring really consists of a set and two operations. In the definitions we found it convenient to give these operations a name. So we said that one operation is addition and another one is multiplication, but in reality it could be a different set, a different pair of operations. So for example, we will see semi-rings in which the plus and multiplication are replaced by max and multiplication, or min and sum, min and addition, where max is maximum and min is minimum, and you view both maximum and minimum as an operation on two elements. Okay. So the final, so we have listed properties under addition, under multiplication, and of course since we have labeled this the generalized distributive law, not surprisingly there is a requirement that multiplication distribute over addition. So that is the third property, namely that R under plus and dot must satisfy the distributive law. Namely that A times B plus C is AB plus AC. So these are the requirements on a semi-ring. Alright, so again to recap, you need that all the axioms of a group with the exception of the additive inverse are required, and then under multiplication again you require closure, associativity, identity element, commutativity. You do not require an inverse, but you do require that the distributive law hold. Now, so as far as examples go, the first and obvious comment, I mean if you go back to our discussion on rings, remember we drew a figure like this, a hexagon in which we placed at the top rings, a general ring where you have closure, you have associativity, and you had the distributive property. Okay. And then we had on this side we had rings with identity, rings with multiplicative identity, we had division rings, we had commutative rings, we had integral domains, and then at the bottom we had fields. Okay. Now, semi-rings can be found within this class, because every ring has all the properties. I mean, in a ring under addition it is an abelian group, so you have all these properties plus the additive inverse, which is not required but is still there. Under multiplication you have all these properties provided your ring is a commutative ring with identity. So, what that means is that here I can put down that so if I take this and this, I will get a semi-ring example. It is a little bit more than a semi-ring because you do have additive inverses, but certainly these are examples of semi-rings. Okay. And fields, certainly if you look at fields, fields have the property that they have rings are commutative, they have the identity and are division rings. So, certainly fields also are examples of semi-rings. Perhaps not so interesting, because the interesting examples come when you just barely meet the requirements. Okay. So, here our examples, we will start off by saying that every commutative ring with identity is a semi-ring. In particular, this holds true for fields. In particular, every field is a semi-ring. So, that means that if you look at the set of all real numbers, that is a semi-ring. If you look at the set of all complex numbers, if you look at the finite field of two elements f2, which is 0 and 1, that is a semi-ring, because all of these are examples of fields. If you look at the set of all polynomials over a field, then that's a commutative ring with identity and therefore is a semi-ring. If you look at the integers is an integral domain. It actually is a commutative ring with identity and with no 0 divisors. So, all of these are examples of semi-rings. Here is another somewhat unusual example of a semi-ring, but very useful. So, here R plus dot is a subset of the real numbers from 0 to infinity under the usual addition and multiplication. So, that means that on the real 9 we are only going to take the set of all positive real numbers including 0. So, this rectangular brace here means that you are actually including 0. Now, why is it okay? So, this is meant to represent the real line and this is just nothing but 0. Now, okay, let us just make that a little bit shorter so that you do not think it is an axis or anything. Right. Now, you might say, why is it that you take a subset of the real numbers? It turns out that, at least insofar as applications to coding theory are concerned, what you are working with are either probabilities or else scaled versions of probabilities, and the scaling is done by a positive real number. Now, any probability is a real number lying between 0 and 1. When you scale it using a positive scaling constant, it will lie between 0 and infinity. So, that explains why you are restricting your attention to 0 to infinity. Okay. And then since you are working with real numbers, the addition and multiplication come in a natural way. So, now how do we actually show that this is a semi-ring? So, to show that this is a semi-ring, we need to make sure that all the axioms are satisfied. So, let us check that. So, if I look under R and plus, then I notice that I have closure, I have the associative property. Do I have the identity elements? What is the additive element? Well, the additive identity is 0. That is why we have taken care to include 0 explicitly here. So, yes, we do have the identity element. And then, of course, addition is commutative. So, we meet all the requirements here. So, there is no problem. Then let us look at R under multiplication. Let us look at R under multiplication, and again it is easy to check that we have that it is closed under multiplication, that multiplication is associative. There is an identity element which is just 1, the real number 1, because after all the real number 1 is sitting in here. So, it has the multiplicative identity, and multiplication is also commutative. So, you also have the commutative property, and we also know that the distributive law holds. Okay, so, all the axioms are actually satisfied. So, this is an example of a semi-ring. So, I think this is a good place to stop. We have about a couple of minutes left only. So, just to recap, what we did today is we started, I just completed our discussion on convolutional codes by actually clarifying the meaning of the term D-free, which appeared in an expression from the last lecture. Then after that we started our new topic, which is the generalized distributive law, and the generalized distributive law is the application of the ordinary distributive law, perhaps in settings that you would not have thought of earlier, and the application is towards, for our purposes, for the purposes of this code, is for decoding error correcting codes. However, it turns out that the same distributive law can actually be used in other settings. As I mentioned the term belief propagation. So, belief propagation has applications not just to decoding of codes, but also for sensor networks, for example. So, we started talking about the GDL, and then I told you how the distributive law can achieve a savings in computation through some simple examples. And then we went a little bit mathematical, and I said, well, we would like to put it on in the right algebraic setting, which turns out, which from the viewpoint of a certain paper is the setting of semi-rings, and semi-rings are very much like rings. The only difference is that you are missing the additive inverse. So, we defined what a semi-ring is, we looked at some examples, okay, and we will continue the examples and continue our discussion of the GDL next class. So, thank you.